Last video, I talked about score function. Of course, score function is highly connected to facial information. Okay, so I think I'm going to have a quick review on score function before moving to facial information. I'm going to walk us through example, okay, how we can obtain a score function from a distribution and how we can show that the expected value of a score function equal to 0. And of course, expected value of a square of score function is the facial information. Okay, give me 1 second. I'm actually going to start. I'm going to share my whiteboard. Okay, so a quick review in my last video. Score function is the theta. Okay, lane f of s given theta. Okay, the score function actually measures sensitivity. Okay, of f of s theta. So that's why you see that we're differentiating the natural log of that with respect to theta. And of course, I was able to show in my last video that expected value of x equal to 0. And not only that, I also able to show that expected value of s squared is the same thing as the variance of s and is the same thing as expectation or d the theta. Okay, ln f of s or theta or squared. Okay, that we also call facial information. Okay, and I remember I said in my last video, facial information measure how much information the parametric probability law carries about the theta. So it's more or less like talking about the amount of information the data carries about the parameter of interest. Okay, so we all know that, but I'm going to walk you through example right now. Okay, so for instance, we have if we got x follow normal distribution with mu and the variance is already known. Okay, so when the variance is 1, okay, we want to figure out mu. So that is telling you mu equal to theta. Okay, so if I want to write f of s given theta now, don't forget I said my theta is mu. Okay, it's going to be 2 raised to power, 1 over square root of 2 pi exponential raised to power minus r. Okay, then gonna have x, okay, minus mu, okay, all squared. Okay, so that is because the sigma square is 1. So this is what we're gonna have. Okay, so if I want to find the score function of this distribution, okay, so what I'm actually gonna do is my score function is gonna be d theta. Okay, the theta or ln f of s, okay, of that. So which means I need to first write the ln natural log of the given distribution. Then after that, I'm actually going to differentiate with respect to theta, okay, to be able to get my score function. Okay, so this is going to be d theta ln into, okay, 1 over square root of 2 pi, okay, exponential raised to power this. Okay, I'm actually gonna this is what I'm gonna have. And the moment I have this guy right now, so I need to simplify what is inside before I even differentiate. Okay, and don't forget, like I said, the mu here is actually theta, as I mentioned that here. Okay, now before differentiating that, I think what I need to do right now is to first, like, I'm gonna write d theta, d theta, then into, ln, okay, this guy now, I can write that as 2 pi raised to power negative half, then exponential raised to power negative half x minus theta squared. Okay, so this is going to be d theta. Okay, I'm actually, if you apply the logarithm of the product, I'm actually going to have ln 2 pi, okay, raised to power half, okay, and this is going to be negative of this, okay. Now if I have that guy now, okay, I'm actually going to rewrite this as the theta, okay, into 1 over 2 ln 2 pi minus half into x minus theta all squared. Okay, so if you take a look at what we have now, okay, we can differentiate with respect to theta. Of course, this is going to be 0 because that's a constant that doesn't depend on theta. Okay, we're going to differentiate this guy with respect to theta. Okay, so minus half, or 2 is going to come down. Okay, differentiating inside because that's a composite function. That's going to be -1. Then I'm going to have x minus theta. Okay, so when I have s minus theta, so what I'm actually going to have, this core function here is actually x minus theta. Of course, I showed you the other time, expected value of a score function must be 0. Okay, so let's see. Okay, all what we're going to do is to uh, you know take the expectation of both sides. Okay, expected value of x equal expected value of x minus theta. Okay, which is going to be expectation of x. Expectation of theta is theta, and expectation of x equal to theta. Okay, theta minus theta, that will be 0. Okay, so which confirm that the expectation of a score function is going to be equal to 0. Okay, now if I also want to find, now that I've already found the expectation of a score function equal to 0, okay, can I also find Fisher information? I actually want to know the amount of information in the data, okay, that the data carries about the parameter of interest. Okay, so actually want to do expectation of s squared, which is also variance of s, which is the same thing as Fisher information. Okay, now if I actually want to do that, so what I'm going to do is to find the expectation of s squared, and don't forget, I've already found the s coefficient to be s minus theta. Okay, what I'm just going to do is x minus theta all squared. And what is that? Okay, expectation of a random variable minus theta all squared is the variance. And what was the variance given in this problem is 1. So expectation of s squared equal to 1. That's what we mean. Okay, so that is how to get our Fisher information. Okay, the last example I'm going to do on Fisher, on this is, if I want to get a situation where two parameters, I got a probability distribution where two parameters are unknown. Okay, maybe I'm working with x follow normal with mu and sigma. Okay, now f of s is actually going to be 1 over square root of 2 pi sigma squared exponential raised to power d is x minus mu over sigma all squared. And in this situation now, our parameter is actually mu and sigma. Okay, if our parameter is mu and sigma, we're having a multi-parameter situation. We're actually going to get two form of a score function. Okay, now what my s is going to be, okay, on now, okay, I'm actually going to use a score function. I'm going to have the theta high, okay, ln f of x theta. Okay, so which means the number of score function I'm actually going to have, we go from 1 to 2 because I got mu and standard deviation. Okay, now the next thing I'm actually going to do, okay, is to rewrite the distribution. Okay, I'm going to write the distribution now. Okay, f of s given mu and sigma. Okay, so this is 2 pi sigma squared raised to power minus half exponential raised to power x minus mu. Okay, now you remember the other time, um, if I want to get a score function, let's say I want to get the score function one at a time. I want to get a score function that has to do, maybe I'm going to call that one x1. Okay, the one that has to do with mu first. Then I'm going to get a score function that has to do with the standard deviation. And I'm going to do with respect to standard deviation, f of x, mu, sigma. Okay, it means I'm actually going to get two score function. And when I get two score function, I'm also, by the time I do expectation of s squared, I'm actually going to get two Fisher information because we're seeking information about two parameters. Okay, so I'm actually, if I for first get with respect to mu, okay, I'm just going to have ln 2 pi sigma squared raised to power that exponential raised to power that. Okay, now what I'm going to do now, I'm actually going to rewrite that. Okay, I'm actually going to rewrite that. Okay, so the first score function now, d mu, okay, um, that's going to be negative half ln 2 pi sigma squared minus half, okay, x minus mu squared. Maybe I can do sigma squared, okay. Now, when I have this guy now, I'm actually want to differentiate with respect to mu, okay, differentiating with respect to mu, this is a constant, right? Okay, so here I got this negative 1, 2, x minus mu, okay, divided by sigma squared. So that cancel that. Okay, the score function is actually this, okay? This is the score function for parameter mu. And if I want to investigate whether, the expected value of that is 0, I'm actually going to have expected value of this, okay, divided by sigma squared. The numerator here is expected value of x minus mu over sigma squared. This is mu. So mu minus mu is actually 0, okay? And if I want to obtain with respect to sigma, okay, I've gotten that if I want to do the second score function, where what I want to do is going to be with respect to sigma. Okay, so I need to be able to write the function very well first. Okay, need to tidy it up. So negative half ln 2 pi negative half ln sigma squared minus this x minus mu all squared over that. So I want to differentiate that now. With respect to sigma, that's going to be 0. With respect to sigma, I'm actually going to have this sigma squared. That will be 2 sigma divided by sigma squared. Okay, minus half. Okay, if it's sigma raised to power 2 go off, that sigma raised to power minus 2. Okay, which is going to be negative 2. Okay, x minus mu all squared divided by sigma 3. Okay, so that is what we differentiated. So this cancel that, okay, and this cancel that. So I'm going to have 1 minus 1 over that. Then I'm going to have plus x minus mu squared raised to power sigma 3. Now, this is the score function. So that is going to be the score function, the second score function. And you know what, you can also investigate whether the second score function is going to be equal to 0. Okay, whatever score function has to be um, equal to, has to be equal to 0. Okay, has to be equal to 0. So let's see. Okay, so we have expectation of x2, okay, so equal, okay, expectation into negative 1 over this plus x minus mu all squared, okay, divided by sigma 3. Okay, so this is going to be negative 1 over sigma plus expectation of x minus mu all squared over that. Okay, so when you have that now, the expectation of x minus mu, that's going to be sigma squared. So right now, you know, I have 1 over sigma plus sigma squared over sigma 3, which is 1 over sigma plus 1 over sigma, and that is going to be 0. Okay, that's to show that so here we got two score function, and the expectation of each of that will give us 0. And by the time you try expectation of square of score function, that will automatically become a feature information. Okay, that's what I have for you. Bye-bye for now.